So now we'll be moving to the next application of Gauss law. The second application we have electric field intensity due to infinitely long straight charge wire. Here we'll consider a uniform charge wire of infinite length having a constant linear charge density, that is denoted by lambda, also as charge per unit length, which is kept in a medium of permittivity epsilon, where epsilon equals to epsilon naught k. Now for the electric charge, here the diagram of a long straight charge wire. From this, in the figure, the electric field intensity at point P at a distance r, from the charge wire. So this is small r from this charge wire at a distance point P. Let us imagine a coaxial Gaussian cylinder of length L and radius small r, where it is close to each end by plane of caps normal to the axis, passing through the point P. Consider a very small area ds at the point P on the Gaussian surface. By symmetry, the magnitude of the electric field will be the same at all the points on the curve surface of the cylinder, and will be directed radially outward. So we can have, by symmetry, the magnitude of the electric field intensity will be the same at all the points on the curved surface of the cylinder and will be directed radially outward. Now, therefore, the angle between the direction of electric field E and the normal to the surface of the cylinder ds is 0. That is, cos theta will be 1. So angle between E and ds will be 0. Having this, therefore, since we have E dot ds equals to EDS cos theta, where it also can be written as EDS, where cos theta, since we have 1, so we can have, that is, flux d phi through the area is given by E into ds. So the total electric flux through the Gaussian surface would be given by flux equals to integral of into E into ds, where also given by E integral of ds, where we have integral of ds equals to 2 pi r l, that is for a cylinder the surface area will be 2 pi r l. So we'll have flux equals to E dot integral of ds will be 2 pi r l. So this we consider as equation 1. Now by Gauss theorem, the net flux through a closed surface is given by charge per unit permittivity, that is 2, equation 2. So since we have equation 1 and by equation 2 we'll be having charge per unit epsilon, that is flux, which is also equivalently equals to electric field intensity times 2 pi r l, where 2 pi r l is the surface area. So we can have, and we also have lambda, that is equals to charge per unit length. So by charge will be equals to lambda, that is linear charge density, times the length. So we can substitute lambda in place of q, we can substitute lambda l. So in this equation we'll have, instead of q we'll have lambda into l upon epsilon equals to E dot 2 pi r l. So l and l can be cancelled and we'll have E equals to, that is lambda upon 2 pi r into epsilon. So that gives us electric field intensity due to a infinite long straight charge wire. So this is the value of E, that is for a uniform long straight charge wire cylinder, or the field intensity at due to an infinitely long straight charge wire. One important point to remember: if the direction of the electric field E is directed outward, if lambda is positive, and if it is inward, the lambda is